All right, so in this problem, we're going to be basically asked to compute drag force, and then from that drag force, we're going to compute power. So this is relatively straightforward, but we'll see that it's actually almost more of a Reynolds number problem, because before we even get started, we have to estimate the Reynolds number, and we're not quite given everything that we need in order to do so. So in this problem, we're to find the, we're told that we have a blimp here, and that the drag coefficient, which we're given, is about 0.006 if the Reynolds number is greater than 10 to the sixth. So that tells us right away that we have this data, but we can't actually use it unless we confirm that the Reynolds number that we're dealing with is high enough. Now we're given some more data here. So we're told the length is 75 meters, which is something we need for a Reynolds number based on length. That's great. It has a surface area of 3,400 square meters. Um, and that's helpful because we're told that the drag is based on that surface area. And now we want to estimate the power required to propel the blimp at 18 meters per second at a standard altitude of 1,000 meters. So notice, however, that we're not given the density and viscosity. And because we're at this altitude of 1,000 meters, we can't just assume that density and viscosity are the same as at sea level and standard temperature and pressure, right? So we have, to start with, we have to check, is RE based on L greater than 10 to the sixth, right? So this is our method. Second, we're going to go in and we're going to compute the force to drag, um, and right, we're going to find that drag force is equal to 1/2 CD times rho U squared times A surface. Note that this is not the frontal area. This is not the planform area. This is a different area that we're supposed to use based on what we're told about this drag coefficient. And then 3, we're going to find the power is equal to the force due to drag times the velocity. But so to get started with, we have to compute that Reynolds number. And since we know that we're at a altitude of 1,000 meters, we can go to table A6, which tells us properties of the standard atmosphere, because we know, we're trying to find RE based on L, which is going to be U times L times rho over mu. And so at 1,000 meters, we know, right, here's our density. Right, so we have rho at 1,000 meters is equal to 1.11 kilogram per meter cubed. So 112 kilogram per meter cubed. But now we have to find the density. And if you remember way back to chapter 1, right, again, this almost calls us back to chapter 1 here. In chapter 1, we talked about how the atmospheric properties change with elevation. We also talked about how um, uh, viscosity is a strong function of temperature. And we can see here the temperature is different, right, at 1,000 meters high than it is at sea level. And so now we have to find mu at 1,000 meters. Um, and for this, if we look also in the back of your textbook, just below table A2, there's a summary of kind of suggested laws to use for estimation of properties for air. And it states that we can look at mu over mu naught equal to T over T naught to the 0.7. So mu naught would be our viscosity at room temperature. So we'll take mu naught, we'll say mu naught is going to be equal to 1.8 times 10 to the 5 second squared. T naught, so this is all in Kelvin, so T naught is 293 K. So at 282 Kelvin, so we'll get this mu 1,000 meters is equal to 1.8 times 10 minus 5 times 282 over 293 to the 0.7. And so we're going to get this mu is going to be roughly equal to 1.75 times 10 to the minus 5. Let's put this in Newton second per meter squared. Okay, so now we finally have enough information to compute our Reynolds number based on length. Right, so like I said, it seems a relatively straightforward problem, but we actually have to do some work before we even get to Reynolds number. And we have to check the Reynolds number before we get started because, again, our data tells us that this number is only valid if the Reynolds number based on length is greater than 10 to the 6th. So now check REL, and this is going to be equal to our velocity of 18 meters per second. Our length is 75 meters. Our density is 1.112, assuming everything here is in SI units because we've been working in SI. And our viscosity 1.75 times 10 to the minus 5. Don't forget the exponent there. That's really important. I know I've seen that happen a few times. So 18 times 75 times 1.112 divided by 1.75 e to the minus 5. And we're going to get 8.6 times 10 to the 7. And this is greater than 10 to the 6th, so we're good. Right? So we know that our drag coefficient, we can use the given data for drag coefficient because our Reynolds number meets that criteria. Nothing, you can't just assume, right? You can't just assume just because it's given that it's going to work. I do want to see you check it, right? And that is a key piece of this problem. So if this were, on the exam or something, and you didn't check Reynolds number, you'd be missing out on, potentially a third of the points on this problem. Okay, so the second part is now to find the force due to drag, and we're just going to use our standard expression here, but noting that the area is the surface area because, again, that's how our drag coefficient is defined, and that's how it's given. So we're going to have the force due to drag is 1/2 times the coefficient of drag, which is 0.006, times the density, 1.112 kilograms per meter cubed, times our velocity squared. Velocity again is 18 meters per second, so it's 18 meters per second, whole thing squared, times our surface area, and our surface area here is 3,400 meters squared. So if we plug that in, so 1/2 times 0.006 times 1.112 times 18 squared times 3,400, and then we'll get a drag force of 3675 newtons, right? Okay, so we have our REL up here, our drag force right here, and now to compute our power, right, which is the final thing that we're looking for in this problem, say power. This is just the aerodynamic power, which is really the relevant power that we have here for this blimp. This is going to be a drag force times the velocity. So this is 3675 newtons times our velocity, which is 18 meters per second. And so we're going to get our power, so that whole thing times 18 is going to be about 66,000 watts. And the textbook notes that this is equal to 89 horsepower. Okay. So there we go. Not an especially powerful um, actually motor required. If you think about what you typically find in a car, 89 horsepower is pretty small. Um, so not a huge power that's required to drive this really fairly large blimp. In large part due to its streamlined shape and also the relatively slow speed at which it's traveling. But there you go. So this was an example problem of how to compute drag force and aerodynamic power, or the power required to overcome aerodynamic drag. But you see that buried within this problem was actually a really nice review of computing Reynolds number based on sort of incomplete information that we had in this problem. All right, thanks for watching.